In Chapter 2, we talked about mass number, and we said that mass number was the sum of protons and neutrons in an atom. Atomic mass is a term that commonly gets used interchangeably with mass number, and they really don't mean the same thing. Mass numbers referring to a particular isotope. So if you have a specific isotope of carbon, for example, carbon-14, its mass is 14 for that specific atom, or one atom of that isotope, meaning that there are 6 protons told by the atomic number and 8 neutrons told by the combination of the mass and atomic number. Neutrons plus atomic number. Atomic mass is more of an average. It's also called the average atomic mass. And what it does is it tells you the exact mass of one atom in the nucleus. So when we talk about atomic mass, there are 3 particles that deal with the mass of any subject or any atom. There are the protons, neutrons, and electrons. Protons and neutrons are relatively the same size and each have a mass of about 1 atomic mass unit. An atomic mass unit is a special unit that we use for atoms because they are so small. 1 atomic mass unit is approximately 1.66 times 10 to the negative 24th grams. So you can see how small of a number that is and why it's not practical to talk about atomic mass in terms of grams. So we have a special unit of AMUs. On the periodic table where you see the atomic mass, we have what is called a weighted average. And a weighted average is similar to a class where you have a teacher who tells you they're going to grade the class based on percentages. So for example, they say that 80% of the class is homework, 10% is quizzes, 10% is tests. So each thing doesn't carry an exact weight. So if you get a good score on your homework, which because it's 80% of your grade, it makes a better effect on the average, or it has a greater effect on your overall average. That's what the atomic mass is of an atom. For example, carbon on the periodic table has an atomic mass of 12.01. What that means is the average mass of a carbon atom, when taking into account all isotopes, is about 12.01. If we round our atomic mass on the periodic table to the nearest whole number, it will tell you which isotope is the most abundant on the Earth. So carbon-12 is the most abundant carbon atom that exists. And that's coal, charcoal, graphite, all those things that are very common. Now, how we arrive at that average is very simple. We simply look at the fact that when we have carbon-12, it consists of 2 isotopes. Carbon-12 makes up 98.90% of all carbon, and carbon-13 makes up about 1.10% of the rest of the carbon that exists. So all we do is simply take the average of those 2 things. We take 0.9890, which is the percentage expressed as a decimal, times 12, plus 0.0110, which is again is the percentage of carbon-13 expressed as a decimal, times 13, and we add it up and we get an average of about 12.01. As an example, I'd like you to take your notes and do the example shown here in the practice problems. 2 stable isotopes of boron are boron 10 and boron 11. Boron 10 makes up 19.78% of all boron, and boron 11 makes up 80.22% of all boron. Calculate the average atomic mass. Average atomic mass, again, is expressed as the percentage as a decimal multiplied by the mass. So, if I know that 0.1978% or 19.78% times 10 plus 0.8022, which is the percentage of boron 11 expressed as a decimal, times its mass, 11, and I would simply add those up then, I would get the average atomic mass. And I'll let you finish that up, and I want to see that in your notes whenever I check them. All right, so atomic mass is a number that's very important to us, and it's a number that we are going to use extensively throughout this course. It is a very valuable number. Now, what we're going to refer to it a lot of times as what is called a molar mass, which is yet another name for the atomic mass, or the atomic mass number, or mass number. Molar mass is simply saying that if we have a certain quantity of atoms, what would the mass be? Now, a man named Amedeo Avogadro came up with the concept of 1 mole, and you may have heard that term 1 mole before. I'm not talking about the little animal that runs around the yard. And you may have seen people wearing Mole Day shirts before. A mole is defined as exactly the same amount of substance that is in 12 grams of carbon. Now, what Avogadro did was an experimentation. He found that when you take the mass number or atomic mass of any element if you find how many atoms it takes to get that many grams of the substance, which is a more usable number than atomic mass units, every time he found that that number was 6.02 times 10 to the 23rd. All right, so we call that 1 mole. A mole is simply a quantity, very much like a dozen. If you have a dozen of something, we all know that that means you have 12. If you have a case of soda, we know that usually means 24 sodas. All right, or a pair of pants means you have, or a pair of socks means you have 2 socks. So it's just a quantity like those numbers. We have several analogies. A mole of any element, then, we can say is the mass of that substance. So if I have 1 mole of carbon atoms, I have 12.01 grams of carbon. If I have 1 mole of hydrogen atoms, I have 1.01 grams of hydrogen. The reason why it's important is because it allows us to interrelate things, knowing similar numbers, like comparing apples and oranges. A mole, when chemical reactions happen based on the number of particles, not their masses. So if a reaction happens in a 1-to-1 ratio, that means it takes 1 molecule of one substance to 1 molecule of a second substance. Grams are not convertible, so 1 gram of one thing is not the same as 1 gram of the other. It's clearly obvious by carbon and hydrogen. 1 gram of hydrogen is a mole's worth of molecules of hydrogen, which is 6.02 times 10 to the 23rd molecules of hydrogen. A mole's worth of carbon has a different mass, but it's still the same number of particles. So therefore, we can use the mole to relate different things. So 12 grams of carbon is 1 mole, which is also 6.02 times 10 to the 23rd atoms of carbon. 1 gram of hydrogen is 1 mole, which is also 6.02 times 10 to the 23rd atoms of hydrogen. Now, using these, we can learn how to convert grams to moles, moles to molecules, or atoms. And again, remember the term molecule and atom is simply a matter of what you're dealing with. Atoms are dealing with elements, molecules are dealing with compounds, generally speaking. So the unit you use, the label you use, just depends on what you're dealing with. In your notes, you have a diagram that has 3 boxes in it. And the boxes have in them grams, moles, and molecules or atoms. What this diagram represents is how you get from one thing to another. If you have grams and you're going to moles, you're going to multiply by 1 over the molar mass. Vice versa, if you have moles and you're going to grams, you're going to multiply by molar mass over 1. Again, remember, molar mass is simply the number in the periodic table as seen. If you have moles and you're going to atoms or molecules, you're going to multiply by 6.02 times 10 to the 23rd, which we call Avogadro's number, over 1 mole. And vice versa, if you're going from molecules or atoms back to moles, you're going to multiply by 1 over that number. Let's look at some of these examples for practicality. In our first example, we're looking at 4.87 grams of zinc to moles. So we start by looking at our 4.87 grams of zinc. Make sure we put our units in there. If I'm going from grams to moles, I want units to cancel out. Simple factor labeling or dimensional analysis. From the periodic table, I know that there are 65.4 grams of zinc per 1 mole of zinc. So our units of grams of zinc cancel out. So mathematically now, if I take 4.87 divided by 65.4, I get this big long number. Now, going back to Chapter 2, we again know significant figures play a role here. This is the number I'm using for significant figures because in significant figures, that is the only number that is going to matter. So I have 3 significant figures here. So my number would be 0.0745 moles of zinc. Okay. Likewise now, if we're going from moles of silver to atoms, again, we start with what we're given, 5.14 moles of silver to atoms. 1 mole is 6.02 times 10 to the 23rd. So if I take those 2 numbers and I multiply them out, I would get how many atoms there are. In my calculator, I can't do that because I don't have scientific notation, so you would have to do that on your own. There are two other examples here that I would like you to do on your own and practice these problems.